when I was an undergraduate student struggling to understand what mathematics was all about, uh, like things like what does it mean for epsilon to go to 0 but not quite be 0? Crossing roads in Adyar teaches you that quite easily. Let epsilon be the distance between you and your maker when you cross roads in Adyar. You really understand what it means for epsilon to go to 0 but not quite be 0. And also much more formative experiences of learning mathematics for me was at Math Science as Amri's apprentice about 10 years ago, maybe. So I'm glad to be back to speak here. So I want to talk about the p-adic Jacquet-Langlands correspondence. This is my thesis work at Michigan with Kartik Prasanna. Let me begin by telling you a little bit about the classical Jacquet-Langlands correspondence and what the p-adic version attempts to fix. So here's the classical Jacquet-Langlands correspondence. The classical case is a certain statement about automorphic representations of GL2 and that are the inner forms of GL2. So so G is the group GL2 over Q for simplicity, and H be one of the inner forms of GL2. What this really means is that and in a form of GL2. So what this really means is that it's a quaternion algebra. So it's a simple, it's a central simple algebra of rank 4 over Q. So it's a quaternion algebra. For example, units in so it's units in a quaternion algebra. So quaternion algebra, for example, could be H cross the Hamilton quaternions that you know and love, or it could be something like this. It could be the algebra with this signature. So it's generated over Q by symbols I, J, subject to the condition that I squared is -2 and J squared is -37, and IJ is -JR. Okay. An inner form like this, one way to think about it is that as an algebraic group, it's always, well, at all but finitely many places, it's GL2. And at finitely many places, it's what's called ramified. So it's actually a genuine division algebra. And so the set of places where a quaternion algebra is ramified is an even, it's a set of even cardinality. So this particular algebra is ramified at 2 and infinity. And this one will turn out to be ramified at 37 and infinity, with just some random primes I picked for today. Okay. So what does the classical Jacquet-Langlands theorem say? It says the following. It says that all automorphic representations on H arise from automorphic representations on G. Well, only certain automorphic representations of G will give you ones on H. And so the theorem of Jacquet-Langlands is a condition that characterizes this transfer. So there's the injection. There's a unique injective map from automorphic representations of H into automorphic representations of G. Satisfying the following properties. Firstly, so I was trying to mention that H has a set of places where it's ramified. Outside those ramified places, the local representation has not changed. So if I call this map phi Jacquet-Langlands going to phi, then pi is, so it's an automorphic representation on H. So as such, it has a tensor product decomposition, like so. And the characterization is in terms of these local components. So if V is not ramified in H, then pi Jacquet-Langlands of V should be isomorphic to pi V. The group hasn't changed after all, so we expect the same local component. And pi V is square integrable at the places where H is ramified. So these are the two conditions that characterize the correspondence. Now, this is a very abstract statement about automorphic representations, so I want to give you a very concrete example of what this means. So here's an example. So I want to look at automorphic forms of weight 2 and level 37. Weight 2 and level 37 on GL2. This space you can compute turns out to be two-dimensional. So let me write down their Q expansions. It's of the form Q minus 2Q squared minus 3Q cubed plus 2Q to the 4. I don't need to write quite so many coefficients because it's a small dimension, but let me do that anyway. Like so. And so these are two Q expansions of modular forms of level weight 2 and level 37. I can look at the automorphic representations generated by them. So pi fi be the automorphic representation generated by fi. Then it's a small check that so pi fi at infinity, this component always is determined just by the weight. So if you have weight 2, then the GK module corresponding to it is what's called a discrete series of weight 2. If it's weight k, where k is at least 2, you get a discrete series of weight k. Whereas if k is 1, you get what's called a limit of discrete series. So those are representations of GL2R, and they're just given by one like number. In this case, the weight determines it. So this is a discrete series of weight k, weight 2. And the only other problem prime is prime 37 for these forms. So pi fi at 37, there are three possibilities. It could have been a Steinberg, it could have been a principal series, or it could have been supercuspidal. But its level is not a square, so it's not supercuspidal. And it has trivial Navier-Stokes character. So in particular, no conductor at 37, and the level is 37. So it's really Steinberg for this reason. So this is Steinberg at 37. And at every other place is a principal series representation. Now, these guys are square integrable. A principal series representation is never square integrable. So we can hope to transfer this eigensystem, right? So what you see, these coefficients of Q are the Hecke eigenvalues. So I can try to hope to see this automorphic representation show up on a quaternion algebra that's ramified precisely at 37 in infinity. And this transfer is precisely the statement that these Hecke eigenvalues do show up on that quaternion algebra. And just for some concreteness, I want to write down what this is. So by Jacquet-Langlands correspondence, there exists automorphic representations by JL Fi on a quaternion algebra D, which is ramified at 37 in infinity. Well, so just as you can visualize automorphic forms on GL2 in this via its Q expansion, you can visualize an automorphic form on a quaternion algebra as functions on the symmetric space associated D. But because D is ramified at infinity, it's actually a very simple thing. So it's simply a finite set. So the symmetric space associated with this thing. So the automorphic representation of automorphic forms on D37 infinity may be visualized, well, defined as maybe defined as functions on this adelic thing, but I have to take an adelic, an open compact here. At finite places, I'm going to take the maximal order and take its units. And at infinity, just take the maximal compact. So take maximal compact at infinity. And then d cross q into sim k minus 2. Q bar. Where if so this is a form of weight k. Okay, so automorphic forms of weight k. So if you have a weight k form, you have to look at functions valued in sim k minus 2. So now weight 2, so I should look inside sim 0 of q bar. So that just functions into q bar on this finite quotient. This from our experience in classical theory is simply the class set of the order O. So it turns out, and I did this computation this afternoon, that if I pick a maximal order in this quaternion algebra, it doesn't matter which one, it turns out to have three. It turns out to have three elements, and here are the two forms. If I didn't do my, I think I did my computations right. So the two forms, F1 will transfer to the form 1, 0, minus 1. So these are the three classes in this class set. I have to give you an element of q bar for each one of these classes. For F1, it's 1, 0, minus 1. And for F2, it's 1, minus 2, 1. Okay, so I want to pause here. So this seems like a lot of work to say that you see the same set of eigenvalues on two different symmetric spaces. So what? No big deal. But it is quite important. Here's why. Notice that F1 and F2 are two forms that are congruent mod 2. And the transfers to this quaternion algebra are also congruent mod 2. But by walking through the functoriality door, I have turned congruences between Hecke eigenvalues into congruences between L values. So this is a deep theorem of Wolfs-Paget that on these compact inner forms, these coefficients that come up in the forms are related to L values. And so this is why you really want to have a handle on functoriality for, let's say, GL2. Okay, so now I want to pose the problem that was posed to me by my advisor. It's as follows. Take a weight 1 form on GL2. So here's the problem. So this is my advisor. Take a weight 1 form. So let F be a weight 1 form. On GL2, cuspidal new form, all of that, normalized cuspidal new form. That's also an eigenform. Well, new form means eigenform. So okay, you take such a thing. Then I was trying to tell you that at infinity, the local representation you get is limit of discrete series. So this quaternion algebra that you pick has to be therefore split at infinity. You can't pick something that's ramified at infinity. Okay, but on the other hand, and this is, I'm not going to state much about this because I don't have too much time. But on the other hand, if you take F, it lives in a p-adic family. So in other words, there are systems of modular forms or cusp forms even of higher weights whose Hecke eigenvalues are congruent to F modulo higher and higher powers of P. So if let's say the two weights K1 and K2 are congruent mod P power 100, then I can find a system of I can find a modular form of weight k1, which is congruent to, let's say, 1 mod p power 100, and the Hecke eigenvalues are congruent to that of f mod phi of p power 100, the Euler phi function. So so at least p power 99, p power 99 times p minus 1, right? So at least p power 99. So so here is the problem. The Hecke eigenvalues of f are p-adically close to forms that transfer to D cross, that transfer to quaternion algebra ramified at infinity. But there is no classical automorphic representation associated to f on D cross. Now, this is not a contradiction in mathematics because the automorphic representations are complex representations, whereas I'm taking p-adic limits. So there's no reason for them to be compatible. And that also, so how to fix this was the question she asked me. And the answer is, as you rightly observed, well, you're taking complex representations and taking p-adic limits. So that's the reason for this problem. So you should really work with p-adic representations, or in other words, p-adic automorphic representations. So I will end my talk by trying to tell you what a p-adic automorphic representation is, and why it should, why by definition of such a gadget should be called a p-adic automorphic representations. So that's I hope I have. Okay, 2 minutes. I'll just say quickly what I want to say. So here's the definition of. So solution to this problem. Define a good notion of p-adic automorphic representations. Okay, more concretely, here's what you do. So let's say f is a classical form of weight k. I won't make any assumptions about the weight yet. So when I say classical, I just mean that it's not a p-adic modular form, although it could be p-adic, but it'll complicate what I have to say. So let me stick to the case of classical form of weight k. So let rho f be the Galois representation associated f. And pi f be the automorphic representation generated by f. Now I'm going to start from pi f and try to cook up something p-adic. And so I was so it's really quick, I promise. It's as follows. So pi f, has a tensor product decomposition, like so, of local components. These are a priori complex representations, and the guy at infinity is particularly gnarly because it's defined in terms of some analytic things. And as I was saying, I have problems with letting things go to 0. Epsilon go to 0 is a problem for me. So I will make it algebraic as follows. So pi f infinity, if it's a discrete series of weight k, I will take the symmetric representation, this guy that came out. So I'll twist out the representation at infinity and move it to p. So far, no change at infinity and p. But at p, I take this guy, and then I look at sim k minus 2 of, let's say, qp bar. Okay, if it's a weight k form. Now, if k is equal to weight 1, yikes, what's sim minus 1? Okay, so we don't have a problem there too. But let's hold on to that thought for a minute. There's a way to fix that. When you notice that this is a smooth representation, and I've tensored it with something algebraic. So it's locally constant, and I've multiplied or tensored it with something locally algebraic. So this tensor product will be, well, this is algebraic, this is smooth, so this is locally algebraic. And remember, I want to be able to take p-adic limits. So limit of locally algebraic things need not be locally algebraic. So they're only analytic. So I really should complete this space also. And here's where the p-adic local-Langlands correspondence comes in and magically saves the day. So what I will do is notice that these local components are related to rho f. They are nothing but the local-Langlands correspondent of rho f at v, the p-adic local-Langlands correspondent. And at p, I should take a completion, but it turns out that really what I mean is I should take the p-adic local-Langlands correspondent of rho fp. Now this is a p-adic local p-adic automorphic representation associated to the Galois representation, a global Galois representation. Okay, so now you might ask me, well, you've written a tensor product. Who on earth gives you the right to call it a p-adic automorphic representation? So I should give you that. I should tell you that there's a global glue, but it's the global glue comes from another theory, the theory of completed cohomology, so which I don't want to get into. But I will say that these guys are related to p-adic automorphic forms, and in particular, there is one of these for a weight1 form. So we've now made a transfer of a weight1 form on GL2 to D cross via this witness, namely this automorphic representation. So I will stop here and look forward to your questions. Right. Yeah. So that is the at P, you need something supercuspidal because the p-adic local-Langlands correspondent, when the representation is a principal series, it collapses it to kind of you get something degenerate in that case. So in that case, the p-adic local-Langlands correspondence is not the right thing for principal series representations. So that's why it doesn't vary well in families. So there are some problems like this. So that's why the theorem, the method of proof forces me to consider only supercuspidal ones. I show that the correspondence works on a Zariski dense subset, and I want to take limits. But when I do this, only supercuspidal ones behave well in families, whereas the principal series ones, you get something degenerate. No. So I assume that the Jacquet-Langlands correspondence is known for these classical weights. So then there's a Hecke algebra such that it on a Zariski dense set of points, this correspondence is known. And then you have to do some work to massage it. So this is the right automorphic representation. Then I want to take limits in that space to weight1 forms. But when I do that, if the weight1 form turns out to be principal series, then when you take the limit at P, the representation kind of splits. And so it doesn't behave well in families. Whereas if it's supercuspidal, it stays reducible, and the limits turn out to be what you want. So this is a proof by Zariski density.